I don't think I made this title, to be clear. I think this was what was assigned to me when CAMELS dream, but maybe it'll make more sense as we go through it. This is going to be a talk about an extension of the CAMELS project into what we call the Dreams project, which is where we're focused on smaller scales. And so a big thank you to the organizers and for all the folks who participated in the workshop. That's been really great over the past couple of days. OK, so here's the folks who have actually done the work. The team of folks who have really done most of the things you'll see today. And in particular, we've got Jonah Rose over here on the left-hand side. You'll see him next. He's got the talk right after me. A lot of the results you'll see were put together through a framework that he developed, as well as a whole host of folks who have contributed in a variety of different ways, ranging from helping us to develop coherent particle physics models, up through executing simulations, and ultimately also interpreting the results. And so there's a huge subset of folks who are actually here in this room today. So if you have any questions, of course, come talk to me, but come talk to these folks as well. So to start off, I wanted to just take a minute to maybe contextualize some of this work. It's been 10 years since the publication of the first illustrious paper, and this is a time that I think Shai and myself remember particularly well, not only because it's like involuntarily fused into our collective memory, but also because we had a workshop just a couple weeks ago. In case you can't see him, yeah, that's Shai right there in the middle, OK. And at this workshop, we talked about all the great science that's been done with Illustrious. It's really pretty phenomenal. Between Illustrious and TNG, there's now over 1,000 peer-reviewed papers, which is a pretty substantial impact. And I couldn't help but thinking that as we sat through this conference, right, there wasn't a lot of discussion. There was some discussion, but not a lot of discussion of CAMELS-based science, right? A lot of the work that was done was really great work thinking about what predictions were made from Illustrious or Illustrious TNG about, for example, in this case, we're looking at the cosmic star formation rate density, galaxy stellar mass function, quench fractions of galaxies. And there's been tons of science that's been done in so many different ways, right? But what's been so valuable that's been brought forward with CAMELS is now understanding not just what these results are, but what their sensitivity is to the input physics and the choices that you make along the way. Not just what the predictions are, but how they might actually change if we change a little bit our model. Now, to be clear, the whole time we were trying to do this ourselves, right? This is a plot from 2013 in one of our model presentation papers where we had all these variations of the different feedback physics, right? There was no deep learning involved here. We just handed this plot to Shai and asked him to think about it and tell us what we should do next, right? This was not actually like predictive modeling. We actually just looked at the results and then tried to modify the parameters. It's now truly remarkable that instead you can now run a suite of simulations, vary many parameters at the same time, and pick out or predict what results you might get. And beyond that, you can even write down an expression which will approximate what results you might find. Right? We've come a long way. I think that this is super valuable in helping to contextualize a lot of our galaxy formation results. And at the same time, part of what I want to motivate, not just for this talk, but also for the ones to follow thereafter, is that if there are known uncertainties, you should try to bake them into the results of the analysis that you're doing. And I think dark matter is one of those components. Lambda CDM works. It works really, really well. But there is uncertainty about the nature of CDM. And so by running simulations that vary our assumptions about CDM, we can understand the extent to which that might percolate into some of the conclusions that we draw. So what can we hope to learn about dark matter from cosmological simulations? In fact, this is one of the first victories from cosmological simulations. There's this interesting story of a paper that came out in 1980 presenting a tentative detection of electron antineutrino masses in the range of tens of eV. And this was a kind of really tantalizing result, because at that mass range, this could have been potentially a major dark matter candidate. So in 1980, this came out. Immediately thereafter, people began to ask the question, what would be the implications of such a dark matter model? And in fact, the answer is one that we oftentimes recite, but contextually, I don't know that we oftentimes think about it. The answer was that the distribution of galaxies that were recovered from simulations using hot dark matter did not match that which was seen in the real universe. And by contrast, if you instead have a CDM-based simulation, that clustering looks much better. These simulations, by the way, I think were 32 cubed particles, right? They were able to draw those conclusions. Right? Now, by the way, I want to, for the discussion folks, want to maybe incite you guys and build off of something we talked about 2 days ago. The question was asked, will the community basically accept our results? And so I have a question for you. How many of you could rule out hot dark matter? using simulation-based inference alone? Now, you might say yes to that, you might say no, I don't know, but I think it's an interesting question. Previously, that was ruled out by showing, by having a changed initial matter power spectrum, you got a changed distribution of galaxies, which could be summarized in a two-point correlation function, which didn't agree with observations, right? A straightforward line of logic. Can we do the same thing with machine learning-based framework? I think that's a challenge for us. And this is a low bar, but I think we should address it. In any case, now our simulations are much bigger. They also get us down to smaller scales. We now know that while there's many successes for lambda CDM on large scales, there's also tensions that persist at small scales. The evidence we have that supports the existence of cold dark matter largely comes from its success and its ability to match the large-scale structure. On small scales, there persist tensions. Missing satellites is no longer necessarily considered to be one of them. By taking consideration of observational incompleteness, as well as suppression of star formation in low-mass galaxies, that's not considered to be a serious tension, but there's still a host of other potential issues. Core cusp problem, which was talked about earlier today, too big to fail, basically an abundance of massive satellites, the diversity of both dwarf sizes as well as the rotation curves, quiescent fraction of galaxies, satellite planes. There's many potential issues with CDM. Some of these, by the way, are of stronger tension than others. But the question is, can we understand the extent to which these can be addressed with baryon physics versus dark matter? Now, we're at a time where the observations are going to keep getting better. So there's many examples I could show here. This is showing the SAGA survey. SAGA survey is basically pushing out in the volume that it's probing, trying to find Milky Way analogs and look at their satellite populations as a test of CDM. At this point in time, you can see there in the red, they've got about 100 systems, right? 378 confirmed satellites, a number of satellites ranging from 0 to 13, still way below what we know about for the Milky Way and in the local group. But what this is now doing is it's giving us the beginning of a distribution function for what you expect for Milky Way satellite abundances. And so you can draw many conclusions for this. For example, one being that about 30% of SAGA systems host an LMC-type analog. We also know, by the way, that the Milky Way is consistent with being drawn from this distribution, but on the low side. And that's important for us when we're contextualizing the missing satellites problem. So lambda CDM works on large scales. We have rising tensions at small scales. Really now the question is, should we address this with a change to our feedback physics or a fundamental flaw in our understanding of dark matter? Now, I'd argue both of those are potentially viable. We need to kind of understand the relative impact of modified dark matter models and modified baryonic physics models. So one way to do this is with numerical simulations, kind of obviously. We now have an ability to run self-interacting dark matter, dark acoustic oscillation, dark matter, modified initial transfer functions, warm dark matter simulations, and we can map those into actual predictions for the galaxy properties. That's what you're seeing here. But when you do this, there is that complex interplay between the two sectors. And so it's almost like we need some way to understand the relative impact by marginalizing over uncertainty in each, right? That is exactly why we are here, to talk about how we can use large simulation suites to potentially tackle that problem. So what can CAMELS tell us about dark matter? And I've kind of broken this up into talking about first dark CAMELS and then talking about dreams, just because of the progression of the project overall. If we want to address this sort of problem within CAMELS, the first thing we have to do is parameterize our dark matter model. CDM can be considered scale-free, 0 parameters. As we go beyond that, the most natural next candidate would be warm dark matter, single parameter. We write down the mass of the warm dark matter particle. We're able to then write down from that the initial matter power spectrum. If we want to go beyond this, I've taken a page out of Simeon's book. I'm going to write down some Feynman diagrams here so you guys think I've done something very smart. Okay, and I'm going to tell you that based on these Feynman diagrams, okay, based on basically what you might write down about the specific dark matter model you're interested in, you can map that onto a transfer function. And Francis Jan, really, and the folks who have developed Ethos, have then developed a way that we can parameterize that. In this case, we're looking at a 2-parameter transfer function. We call it H peak, K peak, specifying when and where you might have dark acoustic oscillations. So with this, we can then build a framework that will progressively step us from CDM-based simulations through warm dark matter simulations, through ethos, HPK-peak simulations. From there, we can add on self-interacting dark matter. We can slowly but surely build up a sound footing for understanding the relative impact of modifying your underlying model. So the first thing we did was do some CAMELS-like boxes with these warm dark matter models. Okay, so the key thing to take away from this table is we did this at different resolutions. You can see what this does to the structure. As you go to higher and higher mass particles, you get more CDM-like, so your structure becomes clearer and clearer. That's not a time evolution, that's an evolution in the warm dark matter particle mass. And just as a note, everything we'll look at will roughly start with warm dark matter masses at or above this limit. So we're really pushing into the pretty high warm dark matter mass limit. Okay, so what are our results? Well, the first result is we can use field level inference to evaluate the warm dark matter mass, or to infer the warm dark matter mass up to a point. This is showing the result of training a CNN on dark matter density fields, showing the predicted versus true warm dark matter mass. You can see the correlation up to about 10 keV. But resolution matters. So in this case, we're then degrading. We're going from 512 cubed particles down to 128 cubed particles. As you step across this line, you'll see our correlation over there gets a little bit worse, and then a lot worse. It's because, of course, you're shifting your information down to scales that are not resolved by those simulations. The image resolution matters, but somewhat less. So here's what happens if we take our highest resolution simulation and then use less information-dense images. We do a little bit worse, and then somewhat worse. So basically, the most important thing is having really high-resolution simulations, and unfortunately, that's just expensive. We can know something about where that information is held, and this is something that was already kind of touched upon. It turns out, if you use a saliency map or some similar method, you can find that those CNNs, their attention is being captured by the low-density regions. So that's where most of our information is. Unfortunately, that's very hard to probe observationally. And really critically, we can compare this result against what you get from a more traditional power spectrum type analysis. So that's showing a power spectrum for our different warm dark matter runs, or BINS version of our warm dark matter runs. If you try to predict the warm dark matter particle mass from these small boxes, because of cosmic variance, you really don't have an ability to do so. Larger boxes might do better, but the point is these CNNs can actually do better even on these relatively small scales. So what does this tell us about the small scale tensions? Nothing, right? Or at least not much. And the reason for that is that we've not yet gotten to resolving the scales we need to resolve to kind of examine these small scale tensions. These exist at the dwarf galaxy scale. What I've just shown you is using CAMEL-styles boxes, which have limited resolution. And so that's where the DREAMS project comes in. DREAMS project really was formed to find a way to push down to much smaller scales. Brute force method of going to higher resolution isn't really possible, so how can we do this with some other approach? If you're going to have a DREAMS project, you have to have a DREAMS team. Yeah, okay, there's Shai, there's Paco, there's Jonah. Yeah. We didn't bring our uniforms. Okay, so what are we doing? Instead of running boxes, we're now running zooms, right? Straightforward concept. How do you actually do that? You have to have a more involved IC generation step. Specifically, what you're going to do is instead of going straight to generating a box, you're going to first generate a dark matter only uniform density box, okay, something like 100 megaparsec cubed volume. You're then going to pick a target galaxy. For Milky Way mass, if we start with a mass resolution of 5 times 10 to the 9, we can pick that out with 200 particles. That's easy enough. We can't really resolve the Lagrangian region we want to target, so we do a dark matter only zoom on whatever target we pick. Okay? From there, we can define our effective high resolution region and do our full hydro zoom. If you want to go lower mass scale, we can do that, but we first have to have some sort of intermediate zoom process, and I'm not going to say too much more about that. But just to say we have ways that we can go to smaller scales. We have this multi-step process for going to smaller scales. So this is the current set of simulations that are on disk, and I'm going to return back not to this plot, but to this point towards the end, and just say a couple of words about what's going to come next. I'm going to talk about the warm dark matter Milky Way zoom-in suite. Jonah's going to talk about the cold dark matter Milky Way zoom-in suite, but we've also got dwarf scale simulation suites and mass varied suites, which are either going or planned. Okay, so what does this look like? Well, this is an animation here honestly starts out pretty fuzzy. I think the ending part of this animation is much more impressive than the beginning. But to give you some context for this, this galaxy is going to be resolved. It's a Milky Way mass galaxy, and it's going to be resolved at a comparable level to TNG 50. Right? So if you've seen those animations from TNG 50, that's what you should kind of picture in your mind here for the gas distribution around the system. When we zoom in and rotate around it, though, you'll realize we do have quite a bit of information about the structure of this galaxy. TNG 50 is not crazy high resolution, but it does give us some information about, how, not just the existence of the galaxy and its colors, but actually some information about its overall structure. We don't just have one galaxy, but as we zoom out, we're doing this for 1,000 simulations at the same time. Each one of these galaxies has a different warm dark matter particle mass. Each galaxy within this suite also has a different sampling of the TNG physics. And we use a similar sampling to what was used within the CAMELS suite. So what can we do with this? There's a couple of obvious applications. One is that we can capture information about the satellite properties. So in this case, we're looking at the difference between using an emulator to calculate the actual distribution of satellites, or basically the abundance of satellites above a given mass threshold. You can compare the band in this plot versus the sort of grayish band versus the red lines. That's looking at a direct calculation of the abundances versus using an emulator to get those distributions. And I'll kind of advertise, but he can advertise for himself as well, Tree's work, which will be presented tomorrow, which developed this NIHAD framework. It gives us a more involved, a more accurate way to actually understand the abundances of satellites in a given halo. From that, we can then begin to ask questions which are really fundamental or really important to our overall investigation, including what's the abundance of satellites that we have as a function of mass scale? So what's our satellite mass function look like? And then what's the dependence on the various input physics that we have? And so you can see on the left-hand side the dependence on the warm dark matter mass. Going to the right-hand side, our favorite varied parameters. Now, I'm just going to quickly highlight some of the key results we found so far. Or a lot of this is actually still work in prep, so just kind of a little bit of a hint of what's to come. One of the first things we can look at is by Cassidy Coleman. So she's here in the room today, and you can ask her questions about this. Cassidy's been looking at the abundance of LMC analogs around these Milky Way systems. This is highly related to the too big to fail problem. Saga tells us that about 30% of these systems should have Milky Way analogs. The numbers from Cassidy are shown here. There's a couple of different cuts here, but the number that you should compare against is this one here, right? The mass-based cut, or a velocity-based cut, which is telling us we find that number to be closer to about 60%. So we find, there's a lot of systematics to still be worked out on this, so I don't want to overstate this result too much. But there's a factor of 2 offset between the abundance of LMCs that we effectively find in our simulations versus what's actually present in Saga. A second key result that we can dig into is D and J factors. So D and J factors are coming from the particle physics community. Effectively, what we want to understand is we know that if we look towards the Milky Way center, we see the Fermi bubbles, and we see similar signatures. And these could be potential signatures of either dark matter decay or dark matter annihilation. The problem is that the extent to which we expect to see those signals will depend upon our inner dark matter profile. If we have chord or cuspy profiles, we're going to get quite different signatures, especially for an annihilation signal which scales with density squared. So what we want to understand is, to what extent are these D and J factors sensitive to, again, the model that we adopt, as well as the input physics. And so this is work being done by a grad student at UVA, Alex Garcia, where what you're doing here is you're swinging around and using some opening angle cone, looking towards the center of the galaxy, looking at the density profiles along that line of sight, and then calculating the D and J factors from there. So what this lets us do is it lets us make not only a prediction for those D and J factor values, but understand, again, their dependence on modifications to the dark matter. This matters in the warm dark matter scenario. This matters even more in the self-interacting dark matter scenarios, which we will come to in our project, not today, eventually. And then this result, which I think is particularly interesting, though I have to admit it's also, again, early stages on it. This is showing work from this undergrad student, Ilham Leisher, who's currently looking for RUs after his junior year, right, and will be applying to grad school next fall. What he did was he took the merger trees out of these simulations. Each merger tree can then represent a graph, which you can train a graph neural network on to try to understand something about whether that contains information about the warm dark matter particle mass. This is pretty remarkable this works at all, right? Those predictions on the right-hand side are showing the prediction from an individual merger tree graph. Now, what we can do with this is we can attach a lot of information to the nodes, especially things like satellite count, masses, things like that. Right now, all we've included is halo mass. But we can include other features to understand really what might actually be present that can tell us about warm dark matter particle mass. Now, in fairness, this is wildly unobservable. So I'm not actually proposing this as like a serious way forward. What I am saying this for, though, is that if that information actually can tell us about the warm dark matter particle mass, if that merger tree has that information, then it's likely that some distribution of galaxies that we might represent through a graph in space as opposed to in time would do similarly well. We've got work going on along those lines also. Now, this method or this technique can also be applied to other problems of interest that lets you find specialized systems. So that could be higher mass or lower mass systems, but in particular, we've got a project going on with a grad student at University of Victoria, Shoshona Bryn Mamahit, where she's looking at, there we go, galaxy mergers. Terrible video to start, but hold on, it's going to get better. What she's done is she's found merging systems, and then she concentrates all her snapshots right around the time of the galaxy merger. So we haven't talked about galaxy mergers much at all in this particular conference, but to the extent these are drivers of galaxy formation, this sort of approach will let us assemble a population of Milky Way mass mergers that goes wildly beyond what's present in a simulation like TNG 100. These are relatively rare events, and so seeking them out requires sorting over a pretty large volume, and she's got an approach which will let us build that up pretty effectively. So if you look at what we're going to do going forward, you have to kind of navigate through this parameter space. Each column is sort of a choice you have to make along the way in assembling a dreams-like simulation suite. What I showed you here today is this, okay? Hydro simulations using the Arepo code with the TNG model, varying the astra and cosmology at the same time with the warm dark matter particle mass, or warm dark matter model, on a Milky Way or M31 simulation suite. But we can begin to flush out this space, right? What you're going to hear about next from Jonah is the CDM component of this. We're also, at the same time, running simulations with Ramses and Gizmo, varied cosmology, cold dark matter on the dwarf scale. And so that's going to open up a lot of frontiers, thinking about things like core cusp problem in even more detail, thinking about things like the extent to which bursty feedback versus dark matter is influencing our dark matter structure. So just to wind down here, we're excited to get involved with anyone who's interested in doing this sort of either simulation development or subsequent analysis. It's a really unique data set. We're very happy to share that data. A lot of it lives on Rusty in the similar form to what you're already used to using for CAMELS. In addition to that, we're currently hiring a postdoc research associate at UVA. So if you're interested or if you have any students or colleagues who are interested, please take note of that. And with that, any questions? Thanks.
All right, thank you very much. Questions for Paul?
There's Chris back there behind the pole.
Please.
Yeah, this is amazing. I was really interested in the merger tree results. Are there other observables, dependent on that you could, you could do inference on this with? So things like merger rates or the forms of the star formation metal enrichment histories, for example?
I don't know, but you're thinking about it the right way. So the point is you can try to understand what's captured the network's attention in that particular case. Probably has something to do with the abundance of low mass systems, the merger rate of low mass systems. Probably has something to do about the connectivity of the graph. And so I'm not exactly sure what else we might be able to look at, but talking about merger rates would be something we could think about. I also think that if you were to just take a slice of that at a given time, but then assemble many different systems with the same model, that you might have similar information encoded into it. So instead of basically traversing in the time direction, you traverse for a population sense, that you might be able to get something similar out. Of course, a graph is not going to be the appropriate way to represent that. I don't know what is, but that's what we're kind of thinking about right now. Yeah.
Paul.
You go ahead.
Great talk. Just one question. When you were doing the zooms, you mentioned you were doing these 100 megapixel boxes. Do you really need that big of a box to do the zooms?
No. So in fact, we talked about this with Jonah. One of the choices we made, which was, I would have made a different choice for no other purpose but vanity in hindsight. If we had chosen a smaller parent volume, we could have beaten TNJ50 resolution. We didn't. So it depends what systems you want to sample. Okay, if you want to get to groups and clusters, you need a large volume. If you want, there's other reasons why it's nice to have a large parent volume in general. But for our most recent suite, we're using 60 megaparsec cubed volumes. There's no need to have anything larger than that. Well, actually, I shouldn't say that. There may be a reason to have larger than that if you want to sample truly diverse environments. But in general, actually, for this Milky Way suite, we're specifically picking systems that have an isolation criteria away from groups and clusters. So we're probably not losing out on really anything by going to a smaller volume.
So the zoom region is about like 5 times or so the virial radius? Or?
We pick out a region which is 5 times the virial radius. So that lets us have some sense that we'll have limited contamination. Yeah.
Wei Wen?
First is that how do you select those zoom-in samples? Do you worry about that those selections is just random and have some particular features or something like that? The other question is about the silencing map you showed before that is saying that the void, which tell you the most about the warm dark matter, which seems contradicting to me that, right? Because think about you're mostly seeing those warm dark matter effect, which is surprising the structure formation in halos, right? So how do you understand that?
So on the first point about selection, we pick randomly within that space. But the point is you can pick whatever selection criteria you want. So you just got to make sure whatever you're aiming for, you implement that very precisely. In our case, we pick a target halo mass, and we pick a random galaxy that's within that target halo mass, right? Or the closest one to a target halo mass, and that's it, right? So that's for the Milky Way suite. We've also got dwarf suite, which is a different target halo mass. Okay, fine. We've also got a mass varied suite. So again, it's a target mass. For Shoshona's work with the galaxy mergers, we're picking something with a given mass ratio, target merger within a given redshift range, right? Target primary halo mass, right? So you've got like a number of more factors in there, which is fine. The point, though, for the selection criteria is you have to make sure you're precise about what you want and then implement it appropriately. On the point of the saliency map, the voids are useful because you've preserved any information from early times very well in those regions. Whereas in the dense inside halos, you do have information about suppressed small-scale structure, but it's actually not preserved as well as it is in the voids.
Okay, and I think there's a question in Zoom.
Yes, and mine. I can maybe, let me ask first mine. So Paul, we were talking in the break with Tree, and I think there was some discussion that if you go to very, very low mass halos, maybe astrophysics doesn't play a role there. Is that true or not really?
So you're asking the question, like in terms of the small scale tensions, for example?
No, in the sense that maybe at some, you have like a very, very small galaxy. Maybe varying feedback. For instance, agent feedback will not really probably do anything.
Yeah.
But supernova feedback might still always play a role, or?
Well, so I guess what I'd say about that, and this is an argument that James Bullock has been making for many years, Mike Boylan-Colchin as well, is that if you go sufficiently low in stellar mass and you look at basically your energy budget in supernova from that, then you can ask how much damage you can do, for example, in converting the standard NFW profile into something that looks different, and you don't have a lot of energy. So down below to like the ultra faint scale, there's actually just not enough energy to convert a cusp into a core. Now, up until recently, the argument has been that at ultra faint scales, you have cusps, not cores. However, there's actually a paper, and the IAC folks who talked about core cusp formation, I almost asked you about this. There's a paper out of the IAC recently that argued that in fact down at ultra faints you do in fact recover cores. If that's the case, you're right. Astrophysics, when you talk about bursty stellar feedback, could not save you. That's a true statement.
Can I ask this one? So there is a question by Rodrigo. So he says, what are the prospects of also considering modified gravity in the simulations in the next years?
In the next year? The question was reasonable up to that point. But the answer is, maybe I'll just give an answer this way, right? First of all, We're happy to collaborate with just about anyone who wants to collaborate on this. So if you have a code that does modified gravity, come talk to us. Taking another angle on it, as long as there is a way to parameterize some space that you want to sample, and you have an efficient way to actually carry out the simulations, right, then this can be added in. Now, do we have plans to do modified gravity in the next year? The answer to that is no. But if there's people with codes and we can get some computing resources, sure, there's no fundamental block as to why we couldn't. Yeah.
Okay, let's thank Paul again for a wonderful presentation. Thank you. And our next speaker is Jonah Rose, who is going to tell us about investigating the small-scale tensions with dreams.
Great. Okay, so yeah, thank you, Paul, for doing essentially most of my introduction for me. So I'm going to be continuing to talk about dreams and another project that we're doing related to the small-scale tensions. So yeah, Paul just introduced our nice framework to create these galaxies and talked about the warm dark matter suite I'm showing on the left here. I'm going to be focusing on the cold dark matter suite, which is created in a very similar way, but now does not vary any of the dark matter parameters and sticks with just cold dark matter, still focusing on Milky Way galaxies, illustrious TNG physics. So just some kind of brief details on the simulation suite that'll be important for this analysis is that we're sampling the Milky Way mass distribution to roughly cover the uncertainty in the our Milky Way's total mass. So from roughly 5 times 10 to the 11 to 2 times 10 to the 12. And then we vary 5 parameters, 2 cosmological parameters, very similar to CAMELS, but over a smaller range. It's not the full, very large parameter suite that CAMELS does. And then 3 astrophysical parameters. The supernova parameters are the same as CAMELS. AGN is one taken from Shai's SP25 suite that should be more sensitive to the kind of Milky Way mass scale than the one used in CAMELS. And we also have 1,024 simulations. Okay. So to analyze the suite, Paul briefly mentioned this. I'm going to also very briefly mention this because Tree is going to give a talk on this tomorrow. But we use the NIHAD emulator, which Tree developed for the Dream suite, which does a good job at emulating satellite properties around Milky Way mass galaxies. And we can use that to kind of explore our simulation parameters suite. So if you're interested in, more details on how this works and validation and everything, stay tuned for Tree's talk tomorrow. All you need to know for my talk is that I kind of have like a basic heuristic on the right there, which is just showing that the distribution of satellite mass functions between the simulations and our emulator match pretty well. And then we condition the simulator on this on the simulation parameters, and we get out of it some host properties and some satellite properties. And so I'm mostly going to be focusing on some of these satellite properties here. So Paul also brought this up, that there's this recent Saga survey that came out focusing on Milky Way mass galaxies, and is very similar to the selection function of what we do in DREAMS. And it is also targeting satellites, and is a very nice comparison for us to look at. So the goal of this project is to measure some of the same things that Saga did in the DREAMS simulations and see if they agree, how they compare, and how some of these simulation parameters affect the results. So the general plan for this analysis, which we're currently in the process of working on, is to start by measuring various satellite properties that are done in the Saga paper, incorporate the various cosmological and astrophysical uncertainties that we've included in our suite through the parameter variations, include some sort of prior on these model variations, because there will be parts of this 5-dimensional parameter space that are kind of unphysical. So we want to weight this parameter space to be more aligned with current uncertainties on these astrophysical parameters. Compare with Saga results, but then this will be kind of more in the future. We want to actually forward model our simulations into the observable space to make more detailed observational comparisons and place strong constraints on how well these simulations actually match observations. So this is just the part that I'm going to be talking about today. The rest of it is in kind of preliminary steps. So if you're interested, I'm happy to talk about those more later. But yeah, so this is the Halo mass, stellar mass function for our dreams galaxies made with Tree's emulator. This is just for fiducial illustrious TNG physics, so there's no parameter variations done here. And this is the Saga galaxy sample that were plotted. So overall, the selection criteria matches pretty well, although Saga does have some more massive galaxies that are not included in our suite. So part of the analysis pipeline will be to remove those samples to do a more consistent analysis, but that has not been done for the results I show here. So the main thing I'm going to talk about for this talk is this quenched fraction result from the Saga paper. So this is essentially looking at the satellites around Milky Way mass galaxies and asking what fraction of those galaxies are quenched, so they're not star forming. And so Saga did that for their sample and got this measurement, which is at odds with what we've seen around the Milky Way and M31, which is what's shown in the kind of pink here, and also disagrees with a lot of the simulation results that have come out so far. So simulations often agree with Milky Way and Andromeda, and we kind of thought everything was working well. Saga goes, observes 100 other systems, and we find that there's actually this tension, and there's something else going on. So what do we find with dreams when we look at this? Is we find this black band here. So this is, again, just looking at the illustrious TNG fiducial parameters. And we find that around 10 to the 9 solar masses, our results agree quite well. But as you go down to lower masses, you get this disagreement. And this is one of these small-scale tensions that Paul was talking about called the quiescent satellites problem. So the question that we can now ask in dreams is this really a tension that we have between our model and our observation, or could this be explained by some uncertainties that we have in our baryon physics modeling? So, okay. So this is now what these fractions look like if we separate the data based off the 5 different parameters that we model in our suite. So most of them, the supernova 2, cosmology, and black hole physics, don't really have very much of an effect on our results. But the supernova 1 parameter does actually have quite a strong dependence on this quenched mass fraction. So if you don't necessarily trust the exact parameter that was baked into the illustrious TNG model, and you believe there's some uncertainty on that, then that also means that there's probably some uncertainty on this quenched fraction. And maybe this isn't as bad of a tension as we thought. So what does this comparison now look like if we include those supernova 1 variations? We now get much larger kind of uncertainties on the dreams relation, and it seems like it might be more consistent with the Saga results. So this is, again, kind of preliminary, and that we still need to match the selection functions, and then actually make sure we're examining a realistic part of the parameter space, because this might be kind of too large of parameter variation, but that's something that we're going to be looking at. And then this is just kind of one result from the Saga paper. They've also looked at other things like the radial distribution of galaxies, or the like specific star formation rates and kind of other things. So as we build up this pipeline, we'll also be able to compare a lot of our results there and have a more kind of strict kind of stress test of the illustrious TNG and CDM models. And we can also use the other suites in the DREAMS project to explore if variations of the dark matter model also produce any of uncertainties on these relations, and to see if baryons and dark matter can solve some of these tensions we have at small scales. So just the last few minutes I have, I want to go over just some more details on kind of the next steps that we have going on in DREAMS here. So one, Paul briefly mentioned, or is these suites of dwarf galaxies that we're working on. So these will be 3 different suites with Ramses, Fire, and Chang'e, focusing on 10 to the 10 halo mass galaxies at a dark matter resolution of 10 to the 4. So this will be 4 orders of magnitude higher resolution than the CAMELS simulations. And then these will also include parameter variations in each of these models, very similar to CAMELS and the other DREAMS simulations. And it will be a great test bed for looking at these small-scale tensions and a lot of upcoming observations from Roman and LSST that will start to have these low-mass galaxies that we can compare to it with observations. And then lastly, one that's maybe more interesting to some of the cosmology people here is we're also looking at variations to the initial matter power spectrum in these simulations. So Paul talked about our warm dark matter suite, which looks at kind of 1 scale cutoffs in the power spectrum, but we're also interested in looking at some other models that both vary the large scale structure that might be important for things like the sigma 8 tension, or small scale power that is important for these small scale tensions. And then we're also playing around with this kind of unified method where we take a non-parametric model of the power spectrum to make these simulations. We then train emulators and machine learning models on the simulations and can analyze both the large scale models and the small scale models simultaneously. So yeah, just to wrap up, I think the DREAMS project is very exciting in that for the first time, we're able to have kind of these parameter variations and uncertainties at small scales that are important for these small scale tensions. And we can really make much more robust claims on whether a lot of these tensions that have been observed in specific models might be due to just uncertainties that we have in the galaxy formation models, or if there's really some sort of tension that's present between the observations and the theory that warrants some sort of larger shift in our thinking of galaxy formation modeling. So yeah, I'll end there. Thank you.
Thank you very much. Time for questions.
Just one question. Maybe you mentioned, but I missed it. When you were changing the Bernoulli physics, like here, what you said, to match the Saga data, that was for the quench fraction, right? And it kind of matches that line. But I'm assuming that you change that, given the other talks, it will also change the whole, maybe like the Milky Way stellar mass or something else. So do you have an idea of like how much that, I don't know, like that comparison is for like the host itself?
Yeah, so this is part of the, kind of the overall analysis plan that I talked about. We're going to do a comparison of the central galaxies against some scaling relations to see kind of what part of this parameter space is reasonable for like Milky Way mass galaxies, and then use that constrained parameter space to look at the satellites. For this specific plot, this is just varying the supernova 1 parameter by itself. that's generally kind of okay. That shouldn't really mess things up too much. Is when you start varying multiple parameters simultaneously that you start to get some really like unphysical things that we want to take out. So once we do that more complete analysis, this might change like a little bit, but it shouldn't be anything too drastic. Yeah.
Okay, next I think we have a question either Chang, you know.
It's kind of similar to the previous question, but have you looked at whether the supernova feedback parameter that you need to match Saga, how that would look like for the quenched fraction of like massive galaxies overall? Because cranking up supernova feedback will presumably affect that, or the star formation main sequence or something like that.
Yeah. So I mean, that's definitely a good question. I haven't looked at it, but I think that's definitely comparing, the kind of parameter space that we're interested in to other observations, like the star forming main sequence or the or clusters, to make sure both that it's reasonable with other observations, but then also to see kind of what results it has there is very interesting. But we haven't really done that yet.
Okay, so next question is either from Zoom or from Paco.
From Zoom. So Ben Oppenheimer, so it is interesting to see the Milky Way having a statistically higher satellite quench fraction than Saga. It makes one wonder if our halo has a more massive hot halo than typical. Is there any approach using DREAMS to look into this?
Yeah, definitely. So yeah, it's an excellent point. There's kind of a few different things that make the Milky Way special. One being the presence of the LMC, another being a kind of quiet merger history. But it could also be something like the uncertainty on the mass estimate. It could be higher. But so right now in this analysis, I'm matching the kind of selection function to the Saga hosts. You could definitely redo this analysis and match your selection function to properties of the Milky Way, and then see how the DREAMS data does predictions there. And it'd be very interesting, and you would probably learn a lot. So yeah, excellent point, but we haven't done it yet.
More questions? Yes, over there.
Hi, I'm curious from the perspective of Saga systematics. Are there known biases that would cause you to be more likely to observe less quenched galaxies or like satellites, or are you thought to have like a fairly representative sample of satellites for Saga?
Yeah, so it's a good question. There are other systematics that Saga imposes, such as not having super large satellite galaxies. They have an isolation criteria, and they have a couple others. But overall, from what I've been able to look at, our data sets should be pretty similar. But I've done like a preliminary cut on the data, and it seems like roughly 80% of the Saga systems are still present if we completely match the selection criteria that they use. So I don't know, from that, I don't know of anything that really explains this offset. It'll just kind of change things on the margin.
Maybe one question from Ken and then Zoom.
Maybe this is a bit off topic, but I saw all of your curves have this little upturn at the very high mass n. Mm-hmm. And I wonder if that is related to any of your feedback models or black holes or whatever.
Yeah, so I know that the kind of uptick is present in the observational data, not from Milky Way satellites, but looking at just centrals. As you go above 10 to the 10, or around 10 to the 9, 10 to the 10 is kind of the peak of your star formation. And then you get quenching from black holes, I think is the main one. So I really haven't looked at that part of the data at all, so I don't know what our data says about it. But especially given the kind of spread in the data that we have in dreams, it seems pretty consistent with observations.
Okay, thanks.
So there is another question from Rodrigo. So thinking about possible effects of IMBH, not sure what that means, in dwarf galaxies, is the black hole seeding model also varying in this suite? I think he's asking if you vary in agent feedback, I think.
So, yeah, I'm not sure if the question is for the Milky Ways or the dwarf-specific suite, so I'll answer both. For the Milky Way suite, we do vary AGN feedback. We don't vary the seed mass at all. That's just fixed to the illustrious TNG one. For the dwarf suite, we're still pinning down the exact parameters, but we are planning to include black holes, and we will probably be varying the seed mass and other AGN parameters.
All right. Is there any last question? If not, let's thank Jonah again. Hi, Giulia. Can you hear me? Can you unmute?
Yeah, sorry. I thought I did, but apparently no.
No worries. Okay, great. So Giulia is going to tell us about the AIDA project. Please take it away.
Yeah, so hi everyone. First of all, I want to really thank the organizers for letting me give my talk remotely when I had to cancel my trip to New York for, serious family reasons. And I really wish I could be there with you all for this great workshop. So indeed, I want to present some first results from the AIDA project or the AIDA simulations, which I think fit quite nicely with the previous talks because we looked at how to model galaxies in alternative dark matter from like another point of view compared to the DREAMS project. So thanks to Paul, I don't really need to, I don't really need to explain why we want to look into warm and self-interacting dark matter, and I guess you all know what the effects are. I just wanted to add that there's other effects that he has not mentioned that are really close to my heart that these models impact, such as, for instance, strong lensing in case of warm dark matter reduces the number of substructure that you can detect in gravitational arcs, and also the interpretation of the Lyman alpha forest is another really big probe that is compared often from observation and simulations. And also self-interacting dark matter, we all know they create cores, but in combination of baryons, they can do more complicated things. So they can lead to cusps, possibly they modify halo shapes. Self-interacting dark matter also is important again for lensing, and in particular for lensing on galaxy clusters, where once again, the satellites of galaxy clusters have a lensing signal that is not really well matched by the simulations, such as the lensing signal in some of the galaxy scale lenses. And finally, as we all know, dwarf galaxies are important for self-interacting dark matter. So thanks to the previous talk, I can skip ahead to how we decided to tackle this problem, which is to run indeed some big simulations with warm and self-interacting dark matter instead of many variation. And I hope our sample will be useful for the community tackling the problem from a different point of view. So when I started working on alternative model, I started also running my zoom-in simulation. So we all know there's a lot of different cosmological simulations in cold dark matter with different codes, different variations, different feedback models, and so on. So I think the problem is how cold dark matter combines with baryonic physics is still not solved completely, many people would say, but still understood quite well. In the field of warm and self-interacting dark matter, we have many zoom simulations, some small samples I even run myself, but there's not many cosmological simulations, so not many big runs. As indeed, so this plot is, at the time I made it, summarizes every simulation existing on a cosmological volume with alternative models. And the colored one are the only ones that also include some variance. So you have the Eagle reruns with SIDM, Bahamas SIDM, the recent small box of the season project, and Tango SIDM by Camila Correa. So clearly, all the great work done on Zoomies is fantastic, but I often was criticized by giving talks and colleagues, and how do you know that the model that works at these scales and the effect that you see at these scales, how do you know what it will do on every scale? Shouldn't we really try to model the effect of worm and SIDM, dark matter on multiple scales? And so this is the motivation. So we wanted to try and fill this gap that it's in this plot. And so the AIDA simulations are 3 boxes. So they're 100, 50, and 20 megaparsec on a side. And so we're trying to, move a bit down and to the right in the plot. Of course, as you all know, there's a relation between the resolution you can achieve and the volume, but we're trying to do the best we can. And all these boxes will be run from the same initial conditions in multiple dark matter models. So far we have 6, and so in with and without the physics of variance. And more in practice, the 50 and 100 megaparsec box are run from the same volumes of the illustrious CNG simulations. Of course, not at the full flagship resolution, because this will be just unfeasible for computing time reasons. And then we'll have a newer, smaller box, which will achieve the resolution of TNG 50. So our 50 megaparsec box is a bit better than the TNG 100. So it's in between TNG 50 and TNG 100. And the 100 megaparsec box is slightly lower than TNG 100. So we have clearly the dark matter only version, the cold dark matter version, but also we have 3 warm dark matter models. So here on the left is just a collection of constraints on the mass, thermorelic mass of warm dark matter. So the lines tell you where the upper limit stops. So all observations start excluding very, very warm models. And on the right is just the classic matter power spectrum at initial conditions. So we have a very warm model of 1 keV, which we are aware it's fully excluded, but we treat it as an extreme case to see what happens when you combine such a different models with baryonic physics, which, sorry, I forgot to mention, it's always the TNG model, so the fiducial model. We don't change it at this stage. We want to see what happens when we combine it with other scenarios. Then we have 3 keV, which is probably already excluded, but at the edge of some constraints. And in any case, it's what has been used in so many simulations that it's good to compare. And then we have 5 keV, which is still in the allowed region. And for SIDM, for now, we've run 2 models in all boxes. So a constant cross-section with 1 centimeter square per gram and a velocity-dependent cross-section, which is the empirical model from Camila Correa's paper that fits the profiles of Milky Way dual spheroidals and at the same time kind of reproduces the upper limits at massive galaxy and cluster scales. So we have overall 6 models for each box, and we have multiple levels of resolution. Clearly, we didn't run all models at all levels of resolution. For instance, the 1 keV warm dark matter model was only run in the 100 megaparsec box, and then at a lower level resolution in the 50 megaparsec, because it suppresses so much the halo mass function that we don't need to spend computing time to reach very, very small scales. But so I'm happy to share some first results with you. So statistically, the first thing they want to look at is the halo mass function. So here is a plot of the dark matter only runs the ratio 0. So nothing surprising. So on top you have the mass function, and the bottom you have just the ratio to cold dark matter. And so without variance, self-interactions, so the blue and green curves, you practically don't see them because they don't make any difference from CDM, while we see the expected suppression of structure for the 3 warm dark matter models that fit quite nicely theoretical predictions in the past. Once you add the variance, so the trends are the same. There's a slightly different in the sense that the amount of suppression in warm dark matter is a bit different, but the overall trend is the same. So thanks to the fact that we have dark and full physics run and all these models, we can look both at the effect of alternative dark matter as a function of redshift and also baryons as a function of redshift to see what happens when this galaxy formation model is applied in these different dark matter scenarios. So for the first thing, so just the effect of dark matter physics at different redshifts. So here, each color is a redshift. So orange, redshift 0, until light blue, redshift 5. And each panel shows you a different scenario. So clearly, and the ratios to CDM. So clearly in the first one, everything is equal to 1. And so we can see that as a function of redshift, then the suppression or the effects of the different models are very, very similar. So this is also consistent with previous simulations by Mark Lovell, who also saw something like this. We can also look at the effect of baryons. So it's well known in CDM that the baryonic physics will suppress by different amounts the mass function at the low mass ends, depending on what the hydro model is. So if we plot the same, so again, same curves, same redshift, but now each plot shows you the ratio of the full physics simulation in one dark matter scenario to its own dark matter only counterpart. And the quite interesting result is that, especially towards redshift 0, all the curves looks fairly similar. So the only one who has departures is indeed the very, very warm 1 keV warm dark matter scenario. But the others kind of work. So the TNG model on this global quantity such as the Halo's mass function has a very, very similar effect in all these models, which you might have expected or not, but in the end, it's a good test of what happens. Something similar happens also if we look at the matter power spectrum. So here is a plot where, again, is the hydro power spectrum divided by the dark matter only power spectrum. So in cold dark matter, we know already from previous work, it was a suppression, especially at redshift 0, of around 20%, around 100 kiloparsec, and the suppression due to baryon starts at 1 megaparsec and then suppresses things up to around 100 kiloparsec, and then there's an increase again. So these are redshift 0, 1, and 3, and then what happens if we look at the other models, we get similar curves, so the details are not exactly the same, but the trend is pretty consistent. So again, the effect of the model on large scale seems to be fairly, on large scales, but on statistical properties seems to be fairly similar, which is in a way reassuring, because another question that I got many times in proposals and talks is, how do you know that the model calibrated for CDM can work also fairly well in other dark matter models? Maybe all the simulations are wrong. And this kind of proves that so far we can believe that our box produces realistic results. Of course, we don't only want to see things that are all the same, we also want to see differences. And so we look into the properties of halos and galaxies, since all these models modify the structure and the distribution of matter inside halos. So we can take our boxes and look at individual halo. And for instance, this is a galaxy cluster in the 100 megaparsec box. So if we look at the distribution of substructure, this is just a cumulative distribution as a function of radius. We see that all models can suppress the number of structures. Of course, warm dark matter, which is the green curve, reduces the number overall. So there's many less subhalos at all the radii, but also the self-interacting models with the redistribution of matter at the center, they also move subhalos away from the very center of the halo. We can look at density profiles, which again here show that the self-interacting dark matter form, as we know, form a core in the dark matter only version, which is the dashed line, but they also form a core in the dark matter profile in the full physics run, which are the solid lines. And so even if the stars, which instead are the dotted lines that dominate a small radii, pull up the dark matter profile, they don't manage to pull it up to the level of the cold dark matter simulation, even at big masses. And so thanks to our boxes, we can do this at on many scales. So here are the density profiles of halos from 10 to the 10 to 10 to the 14 solar masses. So here you have These are the dark matter only profiles. And so the blue curve is the constant cross-section SIDM, green is velocity dependent. So you have cores of increasing size from small to large scales, which we expect. When we add the baryons, we see a similar effect. So the cores are still there. They're smaller, but they're still there at large masses. And instead, at 10 to the 12 and below, we see a small increase of the central density that has been also reported in previous work, but now we can map it as a function of mass. The warm dark matter models, instead, we know they will not create cores at high masses, but they should create cores at low masses. And they do indeed create cores at low masses. And so this happens that we can see that SIDM and warm dark matter really have opposite trends, and that not only the dark matter profiles is affected, this is what I just showed, but just so here, the solid lines are the total density profiles. And you can see that similar effects are also present. So the baryons are not enough at almost any scale, apart from maybe around 10 to the 12, 10 to the 13, to really bring things back at the center of halos. So this will clearly have effects on observables like strong gravitational lensing, which only rely on the density of matter at the center of halos. So these trends in the profiles clearly have an effect, and so we can measure the concentration mass relation. So we recover the trends in cold dark matter, and we can see how in the dark matter only simulation, we have big cores in the SIDM, which means very, very low NFW concentration, mainly because NFW is not a good fit anymore. And then warm dark matter also deviates at low masses, because in this case, the velocity lower the central density. This is in the dark matter only run. In the hydro run, we also see similar results, but they're just not as strong, except maybe for the constant cross-section SIDM. So these are for halos, and I just want to conclude showing you some galaxy properties. So of course we have hydro runs. We want to look at what happens to galaxies. So some global properties similarly to the mass function are quite well reproduced. So this is the stellar mass fraction as a function of halo mass. It looks very similar in all models. So it may be disappointing, but also reassuring. I don't know. So the total mass of the halo stellar mass of the halo is more or less the same as a function of mass. But if we look at how this mass is distributed, for instance, looking at halo at the sizes of galaxies, this is the stellar as mass radius is a function of stellar mass. The trend is all the same. But if we focus on the differences, as in the lower panel, we see that SIDM produces stellar structures that are 20-25% bigger over a fairly large range in mass. And this is particularly clear if we focus on this region. And here on the right are just the distribution of sizes that are lost in the left panel. And so we see that the SIDM models of the green and blue curve really miss all the small galaxies with alpha mass radii lower than 3. So we see effects that appear at very small scales, and I just want to conclude with some nice images to show how many different galaxies we have, and hopefully the work that we'll be able to do in the future. So this is the galaxy cluster from our runs in 4 different models, so CDM, SIDM, constant cross-section, velocity dependent, and warm dark matter. So by eye, you don't see many differences, except maybe in the second panel, the central density is less peaked. And the warm dark matter 3 keV model is not warm enough to really see by eye that there's less subhalos, but there are less subhalos. But we can also look at stars, and here is just a star's density. It's not a mock, it's just a density of stars. And we can really see that in an SIDM model, the dashed circle, which is twice the stellar house mass radius, is much, much bigger than in CDM. We can also look at galaxy mergers. So this is a merger between a group size and a Milky Way size halo. And so it's a dark matter and stellar distribution. And so the merger is happening in all scenarios. The relative masses of the 2 objects are very, very similar, but clearly the timing is different. And so the cosmological boxes will also allow us to look at if delays or speed ups in the structure formation in the different models. And finally, if we move to group and Milky Way scales. Also, interesting differences appear in the gas distributions, which we haven't really explored yet. So this is a group scale. Well, in the non-self-interacting model, there's this rotation patterns in very dense gas at the center that are dissipated in the SIDM case. This may be an effect of self-interaction, an effect of different timings. I don't know yet. But it definitely looks interesting, and the same can happen at a Milky Way scale, where this is just a randomly picked halo at a Milky Way scale, where you see spiral arms in the gas also, but they look different in the different models. So it will be interesting to look at all these galaxy properties. And so, yes, I just want to conclude saying that hopefully these simulations will be useful for the community. They will be made public in a year, more or less depending on when we figure out from where to do the public release. But if you're interested in using them, we're happy to share the data and do great science on multiple scales with this. And thanks.
Okay, thank you very much. Super interesting results. Questions for Giulia? Chris.
Yeah, amazing results. Thank you. I noticed at the end where you're looking at individual objects. Do you have an idea of how susceptible you might be to butterfly effects or simulation uncertainty between the simulation suites in that regime? And how much can you trust the differences, I guess, between the different models?
Yeah, so indeed, that could be I don't know yet, because so far I've looked at more at the global properties that you saw in the dark matter structure. But I selected quite a bit of objects randomly, and things like this. So same patterns in the gas, but different shape is quite common. So clearly, object by object, it's hard to say exactly what is happening, but I believe hopefully we will manage to find some trends. But yeah, I don't know yet. It's true that there could be some butterfly effect, but I don't know. But definitely things like galaxy mergers, this should be just an effect of the fact that in some way the density is different, and so the merging processes are accelerated or delayed, or that in warm dark matter there's less small scale structure, and so structure formation proceeds differently. So we'll try to disentangle all this. We're not yet there yet. But...
Okay, maybe one last question, if there is any, before coffee break. Yes, Victor.
Just one question. When you were comparing the SDSS data with the sizes of these galaxies, is that what are you comparing there? Is it like it's also like effective radius, or what is shown here?
Yeah. Yes.
Okay. That was just a quick question.
Yeah. Okay.
Thank you.
Okay, thank you very much. Yeah, let's thank Giulia again. Thanks.
Thank you.